It's a pleasure meeting you all in another video. In this video, I hope to discuss whether work done is a path function or a state function. As usual, let's go on with some examples to find out. As usual, let us start with very basic examples. A box placed on a table is lifted to some height h. So a work is done on the box. That is given by W is equal to mgh. I hope everyone is okay with that. Now, let's consider the same box being pushed up a plane, up an inclined plane, that is inclined at an angle theta to the horizontal. Let's try to find out what is the work done here. So when you push the box up the plane, you will have to apply a force that is equal to mg sine theta. mg sine theta. So force equal to mg sine theta is applied to a distance of d. Thus, the work done is equal force into distance. The applied force is mg sine theta into d. Consider this portion. You have a right angle triangle, right? This height is h. So, considering that, I'm able to obtain sine theta as opposite over hypotenuse, that is h upon d. Let us substitute here to obtain mg h over d into d. So d and d get cancelled off. You have mgh. Thus, the work done is same. Therefore, irrespective of the path you choose, as far as the lifted height is the same, the work done remains the same. So, work done is a path independent function, is it? Hey, before you conclude any, check this out. A force F is applied on the box to move it across a rough surface. Work done to overcome friction is given by force into d1. How about if you apply the same force F, this time you choose to go beyond d1 and return back to d1. The applied force is same and the displacement is same. So, is work done the same? We know always we will have to do work against friction. So, this portion also would have done some work against friction, and this portion also would have done some work against friction. Therefore, for sure, the work done is going to be greater than F into d1. Work seems to be dependent on path as a path function. One more, check this out. A work is done in a gaseous system from A to B along two paths, one ACB and the other ADB. We know the work done is equal to the area under the graph. So, work done along ACB is greater than work done along ADB. Here also, the initial and the final points are the same, but when the path is different, work done is also different. Thus, the work done depends on path here too. By these examples, you must understand that work depends on path at times and doesn't depend on path at times. It's simple. If it is a conservative field, it is path independent, and if it is a non-conservative field, it's path dependent. So, how can we identify conservative and non-conservative fields? It's also that simple. If the work done in a closed loop is 0, then we consider it to be a conservative field. And if the work done is not 0, then it's a non-conservative field. For example, let's say here the work done to move from here to here is plus W, and from here to here plus W1, and back down, let's say it's minus W, and from here to here let it be minus W1. So if you go through this loop, closed loop, the net work done is equal to 0. Therefore, this is a conservative field. Similarly, when you go in a closed loop, if the work done doesn't become 0, if you go through this loop, your work done, net work done doesn't become 0. That's not equal to 0. And you call these types of fields as non-conservative fields. So now you have an idea on what is conservative and non-conservative field. Let's go through a few examples for conservative and non-conservative fields. Consider a box being lifted to a height h. Here a positive work, positive mgh, is done on the box. And the work done on the box when it moves along the gravitational field is minus mgh. So if you consider this closed loop, the net work done is equal to 0. A charge being brought from a point to another point on an electric field. Here, as it is a positive charge, a positive work is done against the electric field and a negative work is done to bring it along the electric field. In this closed loop, the work done, the net work done becomes 0. So, in these fields, the work done is independent of path. Consider this example. A box is moved from point A to point B along a rough surface. So a work has to be done against friction, therefore it's a positive work. And if the box is moved back to the initial position, here also you will have to do a work against friction. Thus, the net work done is not equal to 0. A work done in a gaseous system from point A to point B, a work is done, a positive work is done, and back from B to A negative work is done. We know the work done, the net work done is equal to this area in this closed loop. Therefore, the work done is not equal to 0. These are non-conservative fields. Here, the work done is dependent upon path.